Hello everyone, welcome to Stat 479 Lecture 15. And so today we're gonna start to go into this final topic or module on graphical models. So we're gonna go over the basics and the definitions of graphical models. And then we're gonna talk about undirected and directed graphs. So those are basically gonna lead to two different types of graphical models. And then we're going to go into them in a little bit more detail. And there's going to be roughly 6 or so lectures on this topic. It's even just defining graphical models is a little bit more involved than what we've done before, but it builds on top of a lot of things that we've already seen. So hopefully we should get to do it. But the next sort of 2 to 3 lectures is really going to purely focus on defining what graphical models actually are. And so just to put things in the context of the statistical framework that we've been returning through throughout this course. So in this scenario, our data is x1i, x2i up to xpi. So I is 1 to n. So we have, again, p covariates or features and n samples. But in this scenario, we don't have a response. So this is the unsupervised setting. So this is the first scenario where we have unsupervised data. And so the statistical model is actually the graphical model, which we're going to spend the next several lectures actually defining. So we don't know precisely what it is. All that we can sort of say about it at this point is that x1i through to xpi, they're all going to form a joint distribution. So f theta here, x1 through to xp is like a joint distribution. That is a graphical model. And then they're independent across the different i's. So you kind of have n samples of these p variables. These p variables potentially are quite highly dependent or correlated, and their dependence or correlation structure will be captured through the graphical model, and that's what we'll be covering in lectures 15 to 17. Typically, we encode these models with parameters, so there are going to typically be parameters in these settings, and we're going to see what they are. Then obviously the third component of our framework is the algorithms or estimators, and so that's this theta hat, which is going to be an estimate for theta, and that's what we're going to cover in lectures 18 to 20. And what's interesting is that all of the prior approaches we spoke about, like linear regression, generalized linear models, and regularization, all of those are actually going to be used for this. And so you might think it's a little weird that here we have an unsupervised setting, whereas the previous three the 3 topics or modules were supervised, but in fact those are going to be very important when we talk about our estimators or algorithms for estimating these parameters theta hat. And then we're going to talk about the analysis also in lectures 18 to 20, like how close is theta hat to theta. And once again, we're going to be building off a lot of the results that we've already seen from previous things. So here, previously, b hat was like a coefficient parameter, so regression parameter. Here, theta is theta hat and theta are going to refer to the parameters that encode the graphical model. So just to remind people what we started to discuss in the previous lecture. So here we're going to kind of get into the definitions of graphical models. And so graphical models have 2 components sorry. No, come on. It's annoying. Okay, that should be good. So it's this. Oh, this is annoying. Okay, hopefully this works. Okay, something's going wrong here. Okay, that should be good. Okay, so there's 2 components here. Is the multivariate distribution, which we've f theta of x1, x2 up to xp. We haven't defined that yet, but we will shortly. And then there's a graph, which is made up of essentially just edges, or I should say, so nodes, and what's going to be important here, there are going to be p of them, and edges. And I mentioned earlier that if we first talk about the distribution, so the multivariate distribution, we have has this multivariate distribution, and one of the very key concepts that we're going to talk about is this notion of conditional independence or dependence. Okay, so we learned that you have xj and xk, j not equal to k, and then S is a subset of 1 to up to P, but not including J or K. So it's any subset. And then we learn what the definition is of conditional independence. So, we can say that Xj is conditionally independent or dependent of xk given xs. So this is a very important concept, where if you know what the s variables are, those s variables that are not j or k, you can say whether xj and xk are independent or dependent. So that's a conditional independence type of scenario. And once again, we wrote up the definition in the previous lecture. To not really going to explicitly try to confirm or prove that this definition holds or not. It's more just going to be our building block for what we're going to talk about with independence or dependence structures and graphical models. So this property of conditional independence or dependence is very much a property of this multivariate distribution. It's to do with probability. And then I'm just also going to introduce this notation. So this is just, there's nothing new here, it's just notation. I'm going to say this sign here means that xj independent of xk given xs. And so similarly, like the extension of that is that xj is this just means that xj independent of xk. So this is when you don't condition on anything. And then if we want to say the converse, we have exactly the same thing, but we put a slash through that through that Greek symbol there. So here we have xj is dependent on xk given xs. Or similarly, then we just have that xj is dependent on xk. Okay, so and so probably the most important thing to just take out of this intuitively, and I did mention this in the previous lecture, but I'm going to mention it again, is that graphical models encode conditional independence or dependence relationships in f theta of x1, x2 up to xp through a graph G. So this is probably just it's just worth kind of just trying to get your head around what this is really saying. So conditional independence and dependence is a property of the distribution, so it's a probabilistic concept, right? And then a graph is, we haven't defined it, but we will shortly. It's just kind of it's a set of nodes and edges, and effectively, the graph is kind of encoding the conditional independence and dependence structures. So, for example, and this is again going back to examples from the previous lecture. So we have, this gender bias in admission example. And what we had there was if x1 was the gender, x2 was admission rate, I guess, and then x3 is the department. We know that we had that x1 was actually independent of x2 given x3, but then we had that x1 was actually dependent on x2. Okay, and so, we could include like the graphical model, graph, I guess, which we haven't sort of defined, so you don't need to know yet where this comes from. It's given by this, so the department had an influence on both kind of the gender and the admission, which kind of induced this dependence between these variables. And then if we consider the second example, so now I'm just sort of getting you familiar with using this notation of independence and dependence. Then this other example of coin flips plus bell ringing. Okay, and it's very easy to kind of write out this whole distribution. So for this one, I'm just going to explicitly write out the whole distribution. So here we have x1 is first coin flip, x2 is second coin flip, and then x3 is did you ring bell? Okay, and remember that so all of these are binary, so I can actually just write out, so what is f theta of x1. There's no theta explicitly in this case, so but we'll see that there will be shortly. And this is because this is a very simple example. So if we look at you can actually kind of express this easily in a table, because there's only 3 variables that are binary. So there's 8 possibilities. So you can either have so I'm gonna say 1 denotes head, and 0 denotes tail. X2 is the same, so 1 denotes head and 0 denotes tail, and x3 is that 1 denotes ringing of bell, and 0 obviously denotes that you didn't ring the bell. So if you have 0, 0, which means they're both tail, then you would ring the bell. If you have 0, 1, which means that they're different, you wouldn't ring the bell. And if you had 1, 0, that would lead to a 0. And then if you had 1, 1, that would lead to a 1. Okay, so there's, in fact, even though there's 8 different possibilities in total, only so this is kind of where you're getting a dependence here, because even though in theory there's 8 different possibilities, because of the dependence there's actually only 4. So only and the reason for that is because if you know x1 and x2, then you know what x3 is going to be as well. So only 4 possibilities, since x3 depends on x1 and x2. So therefore, we talked about the conditional independence relationships we have there. So clearly x1 and x2 are independent, but x1 is going to be dependent on x2 given x3. Okay, and then the graphical model graph, which again we haven't learned how to define yet, but the idea here is just to understand that we've got conditional independence relationships and they can be encoded by a graph. We have x1, x2, and x3, and this is what the graph looks like for the graphical model. And so we haven't learned yet why this encoding kind of happens, but this is what this kind of encoding represents. Okay, so we've talked about we've given a bit of an introduction to this, but we haven't actually defined yet what is a graph. So let's look at graph definitions. So we're going to define concepts as we go, but just to say what a graph is. So intuitively, a graph is a set of nodes or vertices V and a set of edges E. So we're going to use this notation that G is basically defined by V and E. And we're going to let V here be equal to x1, x2 up to xp. So we're conveniently using the same notation for the random variables as we are for the nodes of the graph, because that's exactly what we're doing for graphical models. But here I'm talking specifically about graphs, and these are very widely used concepts. So an edge E is a pair xj, xk, where j not equal to k. And there's two possibilities. E is undirected if xj, xk is the so I guess it's easier to probably just say that E may be undirected or directed. Okay, so for example, if we have an undirected edge, that just looks like, say, xj and xk, and there's no direction in the edge. But if you have a directed edge, then clearly xj to xa is corrected. And note that xj, xk is not the same as xk, xj if you're in the directed edge setting. If you're in the undirected edge setting, they're considered equivalent. Okay, so so that means there's two kinds of graphs that we're going to look at. So a set of vertices consists of a set of a graph G or an undirected graph G, which is VE, consists of a set of vertices x1 through to xp and a set of undirected edges E, which equal to xj xk, j not equal to k. And one thing to note here is that the size of E has to be less than or equal to p choose 2. So you can only have there's only p choose 2 pairs here. A directed graph consists of, I'll again use this notation. Consists of a set of vertices of directed edges Okay, so I'm going to add another layer to this definition of directed graphs. Is acyclic, because this is going to be a very important definition. If exists no path from any node back to itself. Okay, so I haven't actually defined explicitly what a path is. It's probably easier to actually think of the intuition for it. A path just means you walk from that there's you walk from basically along the graph from xj back to itself. So a cycle or path from xj to xj is a set of edges, set of directed edges. Xj, xk, xk, xl, and then we go all the way up to say n, xj. Okay, so x1, x2, x. So this is not, so I'm going to just sort of put so this is not acyclic because it has a cycle, but on the other hand, this is acyclic because you can see that you can no cycles. You can't walk from any node back to any other node. Okay, and so and I'm going to use this kind of shorthand or this acronym DAG to refer to a directed acyclic graph. A directed acyclic graph has no cycles. And in this course, all directed graphs will be DAG. So there are certainly obviously graphs, as we've already seen, that are not that are directed graphs that are not DAGs, or directed acyclic graphs. But in this course, every directed graph that we see will be a DAG, a directed acyclic graph, and that's because it's going to be really important when we talk about graphical models that the DAG kind of allows kind of factorization in a way that, or allows us to talk about the multivariate distribution in a convenient way, whereas when you have cycles, starting to talk about multivariate distributions gets quite complicated. So let's just see some examples. Undirected graph. So in some sense, like the easiest thing to think about is actually the picture, and that's kind of why this whole methodology is used, because the pictures kind of depict things a lot more easily than the math or the notation does. So let's just say that v is equal to x1, x2, x3, and then e is something like, say, x1, x2, x1, x3. Then, you can see that what the graph would look like is this. And this is an undirected graph. So there's an edge from x1, x2, and then there's an edge from x2, x3. So this is our undirected graph. And then, you could have a directed graph, or in this case, it will certainly be a DAG. If you have v equals, so you can use the v set, and the e set doesn't actually change at all. If we have x1, x2, and x1, x3, okay, then this is going to look like. So remember that the direction that the edges point is very important. So whatever comes first is what's being like, that's sort of where the arrow starts. So it's not where the end of the arrow is, it's where the start of the arrow is. Okay. So this is G. And one thing to note is that for DAGs, just like undirected graphs, we have to have the size of the edge set has to again be less than p choose 2. And so you might wonder why you can't have like edges pointing both ways. And this follows from the fact that if you have an edge pointing in one direction, it can't point in the other direction, because otherwise that would create a cycle. So this is something for you to think about, that for all DAGs, we have the edge set size has to be less than p choose 2 here. Okay, and so just to go through our other examples, remember that if we look at the gender bias example, if we go through the gender bias example, remember that I mentioned that the graph there was x3, x1, x2, and then we had this conditional independence relationship that x1's independent of x2, or x1 and x2 are dependent, but x1 and x2 are independent given x3. So you can see here that v is obviously the same, x1, x2, x3, but e is equal to x3, x1, and then x3, x2. And if we look at the coin plus bell example, so these are both DAGs again. So this is again going to be a DAG, a directed acyclic graph. obviously we had these conditional independence relationships. So x1 was independent of x2, but x1 was dependent on x2 given x3. And so our set V here was obviously x1, x2, x3 again. x1, x3, and then x2, x3. So because the arrows are pointing in the other way, so it's exactly the same kind of, you could say that the edges are the same, but they're pointing in the reverse direction. Because of that, that gives you different conditional independence structures. Okay, and so I've just sort of said, so on the one hand, we have graphs that have edges, have vertices and edges. Vertices or nodes and edges. And then we also have multivariate distributions. We have a multivariate distribution, f theta of x1, x2 up to xp. That has conditional independence relationships. Okay, and then the question, the thing is that graphical models relate these ideas. So you can think of this is a graphical models. So it's a mapping between conditional independencies between x1, so this is something to do with probability, and edges or non-edges in the graph G. Okay, so that's really what kind of is going on, and so that's why these graphical models really have these two components where in some sense the idea is we're trying to relate the graph structure to the we're trying to relate the probability distribution to the graph structure. So now I'm going to talk about these two different, there's, for DAGs and undirected graphs, there are different graphical models. So I'm going to cover these separately from now. We're going to end up relating them later, but I'm going to kind of cover them separately. So I'm going to begin by covering, so we'll begin by covering DAGs. So directed acyclic graphical models. And I'm going to use this notation DAGs for that. Even though DAG was also used for the graph, we're going to use that for the directed acyclic graphical model. So So let's sort of move on to discussing this shortly. So um, this is also referred to as Bayesian network in the literature. So I don't know, some of you may have heard this term. If you haven't, it's okay. But it's also, if you read the term Bayesian network, it just means a directed acyclic graphical model. So consists of a directed acyclic graph G and a multivariate distribution. So let me just maybe make this a bit more. V is here equal to the and a multivariate and a multivariate distribution. F theta of x1 through to xp. Okay, and so so the question is, how does how does E relate to F theta? And that's what we're gonna kind of define, hopefully by the end of today's lecture, but possibly going into the next lecture. Okay, so a couple of other definitions. For a DAG, G equals VE with edge E in E. E is equal to xj, xk. Xj is referred to as the parent of xk, and xk is referred to as the child of xj. Okay, so for example, we have that E here is equal to x1, x3, x2, x3. So this again goes back to this coin plus bell example. X1 is parent of of x3. x2 is parent of x3 as well, so you can certainly have multiple parents in this scenario, and you could have more than two parents. And x3 is the child of both x1 and x2. So the next thing that's going to be important in defining our DAG kind of from the distribution is this notion of factorization of multivariate distributions in DAG. So for now, we're just going to drop the parameter. We're going to reintroduce that later. So x1 through to xp has this joint PDF, f of x1 through to f of xp. So by the chain rule, okay, so if you're not exactly familiar with this, just think about just conditional probability and conditional PDFs. So this is the conditional PDF for xj given x1, x2 up to xj minus 1. And so, if you think about, for example, f of x1, x2, x3, you can kind of rewrite this as, f1 of x1. So this is the marginal of f1 of x1, f2 of x2 given x1 times f3 of x3 given x1, x2. Sorry. Or let me just write this out. So we have x1, let me just start again. Okay, so we're saying that okay, so this is referred to as the chain rule. So this is just the marginal PDF or PMF for x1. This is the conditional of x2 given x1. And this is the conditional of x3 given x1 and x2. Okay, and so this is just referred to as the chain rule. Okay, and how that actually connects back to, and I should also point out that similarly, f of x1, x2, x3 is equal to, you could kind of do it in reverse if you wanted to. So both of these statements are true and you would get exactly the same answer. You've probably seen this done with 2 variables before, so we're extending this to 3 variables here. Okay, so so the idea is, you know, which ordering you do does not matter. And if this is confusing to you, just think about the case. It's confusing to you, you should go back to the bivariate case. In the bivariate case, it's hopefully clear to you that this is true. But then, you know, if you want to go to 3 variables, you're just extending the bivariate case basically, and you kind of can keep doing that up to p. And so again, if things confuse you in the multivariate case, going back to the bivariate case is useful. Okay, and so now let's talk about factorization over DAGs. And this is where this notion of parents comes in. A distribution factorizes over the DAG G equals VE if f of x1, x2 up to xp is equal to the product of j equals 1 to p, fj of xj given the parents here of xj. So this fj of xj given x parents of xj is the conditional PDF of xj given its parents. So remember what parents were? It just meant that there was, recall that parents are nodes or vertices pointing to xj. Okay, so now let's go back to our 2 example. So let's go back firstly to the to the coins and bells example. Coins and bell example. So there we have x1 was first coin flip, x2 was second coin flip, x3 was do you ring bell, and so remember that the DAG looks as follows. x1, x2, x3. And so think about the factorization here. And this we can actually calculate explicitly because we know that, we have, this is what our, so the joint PMF probability x1 equals x1, x2 equals x2. So everything's binary here. So x1, x2, and x3 are either 0 or 1. So this is encoded by the table. x1, x2, x3, and then we're going to say probability of x1 equals x1, x2 equals x2, x3 equals x3. Okay, and so we had okay, and so these are all had a probability of a quarter, right? Okay. And then note that P1 of x1 is just, that's the marginal for x1. P2 of x2, marginal for x2. And then P3 of x3 given x1, x2. It's the marginal, or it's the conditional for x3 given x1 and x2. So what you can hopefully see is that probability x1 equals x1, x2 equals x2, x3 equals x3. That's going to be P1 of x1 equals little x1. So this is going to be a half regardless of what you choose, times P2 of x2 equals little x2. And then multiplied by P3 of x3 equals x3 given x1 equals x1, x2 equals x2. Okay, and you can kind of see that that's going to be equal to a half. P2 of x2 equals little x2 is going to be a half, and then x1 equals little x1, x2 equals little x2. That's going to be equal to 1 or 0, depending on if x1 and x2 are the same. Then you're going to get, you can look at this table to kind of see what different values you get. So, this is what we, so this is kind of how you can write this this table as a factorized distribution. And so note that, recall here as well that x1, x2 are parents of x3, and x1 and x2 have no parents. Okay. Okay, so we can kind of write this out as the as this probability of these of each of these conditional PMFs given its given that parent. So here, when j equals 1, we have no parents. So it's just so we just get a marginal. So we just get P1 of x1. For j equals 2, we get no parents again. So we just get P2 of x2 again. And then for j equals 3, x1 and x2 are parents. So we get P3 of x3 given x1, x2. Okay, and so this is the first note that a clear we'll note that here that we have a clear relationship between the distribution f of x1, x2 up to xp, and the graph, or in the DAG, g equals ve through this factorization. Through the factorization, because we have that f of x1, x2 up to xp equal to product j equals 1 to p. Okay. And so now, one last thing to note in this example, we're going to delve into this in a little bit more depth in the next lecture, is that show x1 using the factorization, we can actually also show that x1 and x2 are independent. Since f1 okay, so this will be the last thing I kind of go through quickly. Okay, so we have this factorization. This is for coin plus Bell example. Okay, so note that so what we can do is if we integrate over x3, okay, so that's just going to be equal to and because this is a conditional PDF, this thing's going to integrate to 1, And so we just get f1 of x1 times f2 of x2. So therefore, x1 and x2 independent. So therefore, factorization also gives us the right independence relationship. Okay, and we're going to go through that in more detail in the next lecture. So we've spoken about factorization over DAGs. We're going to talk about how this relates to conditional independence and dependence relationships, which is going to kind of then allow us to talk exactly about how DAGs encode conditional independence and dependence relationships. Okay, thank you. That's it for today.